Okay, we're continuing with chapter 1 in the algebra textbook. In this video, we're going to go through the third section where we're going to be officially introduced to imaginary numbers or complex numbers. So up to this point, I've already unofficially introduced you to complex numbers or imaginary numbers. And in fact, in the opening video, when we started the pre-algebra section 1, we started talking about complex numbers. And I wanted to do that just so that from the very beginning, you could start to have some perspective on this. But as far as the textbook, it isn't until this third section of chapter 1 that you're officially introduced to complex numbers or imaginary numbers. Okay. So again, I've informally introduced you to imaginary numbers, but we never really went into too much depth on where they come from, what their purpose is. All right. But what I've told you so far is that, so in grade school, all the way until you really started algebra, for the most part, the numbers that we work with are on the real number line. You can graphically represent all of the numbers that you're most familiar with in math as being on a line. And it doesn't have to be horizontal. It can be in any orientation, but we typically make it horizontal like this. And it's like the idea is we call them real numbers, are on a line like this. And this works because the definition of a line is it extends infinitely in both of its directions. And that makes sense because you could have, as large of a number as you want, 100 trillion, whatever, and as large of a negative number as you want. So this is centered. The center of this is at 0, and you have all the positive numbers, you have all the negative numbers, and there's an infinite amount in both directions, right? But it's even the case that, like, between, let's say this is 1 here, it's scaled like that. It's even the case that just between 0 and 1, there's an infinite number of numbers. Like you could have 0.7382, a trillion zeros, 586, right? So this contains all possible real numbers. Okay, and then but all of the subsets of real numbers that we talked about, the natural numbers, the whole numbers, the integers, rational numbers, irrational numbers, are all on this number line here. That's just a way we categorize the different types of numbers on this number line. Okay, now, but what I told you was that what we're actually going to be working with is not just a whole line of numbers, but a whole plane of numbers. In the sense that, so we don't say this is the set of all real numbers anymore. We say this is the set of, we're going to call them complex numbers. Okay. At the center of the plane is this 0 point, but now there's this vertical axis, right? Because when it comes to, if you want to have a plane, it's like two-dimensional. It's these two distinct directions, and we call this the plane of complex numbers. And it's two-dimensional because it's like they're distinct in the sense that, well, if this was the xy plane, well, in that case, if you had 2x minus 3y, well, you can't combine these anymore, right? This is fully simplified. These are two kind of independent terms. That's the idea of two dimensions. So you can pick any, from the perspective of like xy, you can pick any point in the plane. And that's a number. That's the idea. It's not just picking any point on a line anymore. Now you can pick any point in a plane. But what's important to realize is that the set of all real numbers, we're not supposed to put an R like this because this is not the set of all real numbers, it's a set of complex numbers, but the number line is contained in the complex plane. If you stay on this horizontal axis, you're in the complex plane. So the set of those subsets of real numbers, the natural numbers, the whole numbers, etc., are in the complex plane. Technically, if you're looking at things as general as possible, then technically all real numbers are complex numbers. And this makes sense because when you think about the properties of it says real numbers here, but really this applies to any number in the complex plane. They're numbers, right? If something is going to be called a number, that what you can think about is that it means that it obeys these fundamental properties of numbers. That's a really, really important idea to realize, the fact that all complex numbers are going to obey these properties of numbers: the commutative, associative, identity, distributive. And I mentioned why this is so important. You might say, well, these are just like basic stuff. Like this isn't dealing with exponents or roots or exponentials or logarithms. Well, no, remember, addition, subtraction, multiplication, and division, and like the distributive property. That's the fundamentals for everything we do in algebra. Like an exponent term, 2 to the 5th, that's multiplication. A root is just the opposite of this. So it's like kind of like, division in a sense. It's the opposite of an exponent term. But an exponential function that we're going to study in a few chapters from now, that's just a power. It's put into a function form, and a logarithm is just the opposite of this. So it's all comes down to, everything we do in algebra comes down to these properties here. And complex numbers and just pure real numbers all obey these properties. That's a hugely important thing to realize. Okay, so now, but what is this extra axis here? What is this extra axis, and why is it like independent from this horizontal axis? Like what is all this? Where does all this come from? Okay, so what they talk about in this opening paragraph here is that there was a point in time where mathematicians wanted to solve equation. Here's the most basic of this, an equation like this. Okay, and if we're just dealing with the real number line, we can't solve this. And why not? Because there's no number or numbers on the real number line that when you square it, you get -1. And really, this problem we can state this problem in more general, in the sense that you could, for any number on the real number line, there's no number anywhere that when you take it to any even power, you get a negative number. That's the overarching issue. But the most basic fundamental form of this overarching issue is, okay, what number when you square it do you get -1, right? That's the most basic way you can look at it. Okay? And that's it. That's it. That's the purpose of why that complex numbers were invented. So we could answer questions like this. Like, you can think about it, there's no need, if there's unanswered problems, then if you're able to go ahead and invent new numbers that could answer those problems, then go ahead and do it, right? But like, okay, but we talked about, what about dividing by 0? Well, that doesn't work out so well, because what has to happen is you have to be able to, like, if you need to, maybe you can like redefine a new, like, kind of like we saw how we could extend to solve the issue of like, what is a number to the -2 power? We could do like a simple extension of what a number raised to a positive integer power meant. That was in perfect math synchrony with the existing definition of like what this meant. Okay, we could think about doing that maybe with division, or we could think about inventing a new number for dividing by 0. But as we talked about, in either case, there's no way to do it. There's no way to do it because you have to be able to invent a number that, if I'm gonna call this the wizard number W, well, it needs to function as a number. It needs to obey all of these properties. If it doesn't obey all of these properties, then it's going to be an issue. Like if you multiply it by 1, you get itself back. If you multiply it by 0, you get 0. If you add it to itself, to the opposite of itself, you get 0. Things like that. If you divide it by itself, you get 1. It needs to obey these properties so it can be a number, right? Well, look, if we define this to be W, the wizard number, 5 divided by 0, or any real number divided by 0 to be the wizard number, well, look, that would imply that W times 0 is equal to some non-zero number. That's a problem, right? However, when it comes to this issue about, well, we'd like people to solve equations to where we're taking a number to an even power and getting a negative number, it was able to just have a new extension, some new numbers invented, and it didn't. They were able to be defined and behave just like regular numbers without conflicting with the existing math. And so that's what they did. And so again, since this is the fundamental, like for the overarching question of, how do we define numbers that when you take them to an even power, you can get a negative number? The fundamental question is, if you want to break it down to its most fundamental, okay, well, what number, let's start with what number when you square it, not take it to an even power, but let's just say the simplest is squaring it, do you get the simplest number, -1? It starts with this. We can start here. And so that's what they did. They said, okay, we're going to define this new number I. Okay, and this is just a number like any other number. It has the same properties of any other number that we've ever worked with. Okay, so what is I? What is I? I is a number. This is the meaning of I. They said I is a number that it's a number that when you square it, you get -1. That's it. That is it. Simple as that. Now, so, okay, here they give, so they give here the definition of the this is the imaginary number I squared is equal to -1. This is the more all-encompassing definition because there's also a definition that says that I is the principal square root of -1. But just remember that this is a principal square root. So it's only returning the positive. So like I feel like this definition is a little more descriptive. They're both fine, but just remember that. So if I squared is equal to -1, but also -I squared is equal to -1 because you've got, we can apply the properties of exponents just like we do, this is just a number. So -1 squared is 1, +1, and we're left with I squared is -1. You see? So, okay. So that's fine, but what's this whole complex plane here? How does this whole complex plane work? Well, okay, so we could say I squared is equal to -1. Okay, and actually just inventing I and saying I is equal to this, I is a number such that I squared is equal to -1, that's enough to solve the square root problem. The idea that, okay, we need to solve equations that are asking us what number when you square it do you get a negative number. All we need is just the definition of I itself, and we can solve that issue because it's like, okay, if we wanted to say what number when you square it do you get -16? Well, the answer to that would be 4i and -4i. Both of these, when you square it, you get -16. Okay, but the problem is that this isn't enough, though. This pure definition of I isn't enough. It's not enough because, okay, let's solve x to the 4th is equal to -16. Okay, so we're asking what number or numbers when you take it to the 4th power do you get -16? Well, okay, you might think, well, 2 to the 4th is 16, so it would be 2i and -2i. Okay, but that's not going to work. And this worked for square roots, but it's not going to work for this 4th root because, okay, what's 2i to the 4th? 2 to the 4th times I to the 4th. 2 to the 4th is 16. What's I to the 4th? I squared times I squared. I squared is -1. Well, that's +16. So as you can see, it's not quite enough just to define that I squared is equal to -1, and really that's all you need. You can just kind of insert an I wherever you need it. That's not going to be enough. And so what needed to be done was to make this to where you could answer any question of what number when you take it to an even power do you get this certain negative number. It had to be defined in this to where it was this whole plane of numbers in the sense that you call this the real axis and this the imaginary axis. Okay, so if you stay on the horizontal axis, you have a pure real number. But if you move off the horizontal axis, then now you have this imaginary component in the sense that, so if we come here, so this is still just like 1, 2, 3, -1, -2, -3, but it's like, okay, this number here in the complex plane would be the number 2 plus, and then it's 1 times I. Okay, this is a number, right? It's like two-dimensional because you can't you kind of look at I. You don't look at I like it's a variable. You look at I like it's kind of like if we had 2 plus pi, right? Well, we can't simplify this anymore if we're going to leave pi in its symbolic form, right? Well, it's the same idea here. We can't simplify this anymore, and that's why these complex numbers are these two-dimensional numbers. But it's going to work out to where now with a complex number, if we wanted to solve if we wanted to answer the question, what number or numbers when you take them to the 4th power do you get -16? If we do this with a certain complex number, I don't forget what this is. Let's say it's, I don't know, 1 minus I, something like that. but okay, this is just a number, so we can take it to the fourth power and distribute and use the distributive property and multiplication like we normally would for any number. Just we can now, but we know that we can simplify powers of I, like I squared or I cubed, etc., because we know I squared is -1. Now, if you took this number here, like this number here, if you took it to the fourth power, and you simplify again, because you could change I squared to -1, etc., what's going to happen is the I part's going to subtract out, and you're going to be left with -16. Again, I'm not saying this is the fourth root of -16. I'm just put this, but that's going to, now this is going to work. Using this entire complex plane of numbers, we'll be able to evaluate any even power of a number that gives a negative number. Any even power or powers, right? There could be multiple roots of a number. Okay? And so that's the idea. That's the idea. Okay, now, so let's see. So they gave the definition of I here. Then they immediately go into this property here, where I mentioned when it came to radicals, the radical symbol, right? This is the principal nth root of a number. I mentioned that while, yes, we can think about taking we're going to learn in trigonometry and in complex analysis we could take any number in the complex plane and find its nth roots, no problem. And we can even find its principal nth root as well, which is what the radical symbol is. However, it's going to, my recommendation was that we don't mix radicals with complex numbers. It's just because I explain in more detail why I'm saying this in trigonometry. We just don't want to be mixing radicals with complex numbers until you get to complex analysis. Then we'll come back to it. Okay. However, we are gonna mix them a sliver, just a sliver, and we're gonna mix them with this property here. Before we get to complex analysis, we're gonna mix complex numbers with radicals here. Okay. Again, when I'm saying we're not mixing them with, I'm just talking about the radical symbol. The radical symbol. So it doesn't mean that we can't find roots of complex numbers. It doesn't mean that we can't find principal nth roots of complex numbers. It's just mixing the radical symbol at this point with complex numbers is going to be a little confusing, so we're not going to go there. In this course, we will mix complex numbers with whole number powers, positive or negative integer whole number powers. We're just not going to be mixing them with radicals. Every time we're dealing with a radical, we're going to assume that, okay, the x is just going to be a real number until we get to complex analysis. And same thing when we talk about exponentials and logarithms, we're going to be assuming, okay, we're never going to be thinking the variable could be a complex number. Not in this course, and not even in trigonometry. Only when we get to complex analysis, we'll come back to that. Okay, but again, whole number powers, there will be problems we're going to look at. Okay, we could have a certain expression, a polynomial expression, and there'd be situations where we'll say, okay, well, x can be, what if x is allowed to be any complex number in the entire complex plane? Okay, but like I'm not saying that this isn't valid to think about x with a rational exponent as a radical, that it's in general, it's not valid to think about x as a complex number. No, it 100% is. Anything that you ever do in algebra, ever, it is absolutely, once you learn complex analysis, x can be any number, because why wouldn't it be? All the real numbers are in the complex plane. Real numbers are complex numbers. So it absolutely makes perfect sense to think about x to the 2/3 as allowing to be any number, real or complex, or log base b of x to be, x can be any number. 100% you're allowed to think about it that way. We're just not going to be going there in algebra or trigonometry. That's it. Okay, the only mixture, the only kind of the sliver that we're going to allow ourselves to mix complex numbers with radicals is with this property here. Okay, it says if b is a positive real number, then the principal square root of minus b is equal to I root b. Okay, so what they're saying here is that when we defined radicals in pre-algebra, the nth root of a, we said that if n was even, if n was even, then we weren't allowed to input a negative number into the radical, because there was no numbers that when you take them to an even power, you get a negative number. We're going to expand this just a sliver. We're going to say, okay, if n not if it's even, but if it's specifically even and it's 2, if it's a principal square root, only that case, then, okay, we'll allow ourselves to input a negative number if we're allowing for potentially complex numbers in the problem, right? Some problems we won't be allowing for complex solutions or whatever, then you wouldn't be able to do this. But if we're opening the door to complex numbers for solutions, then okay, in that case, if it's a square root, principal square root, we'll allow ourselves to input a negative number. Okay, and in that case, we can simplify it by doing this, by taking out an I and now having the positive principal square root. Well, we know how to evaluate this. There's 2 numbers that when you square it, you get 16, 4 and minus 4, but we know that it returned the positive. So this is 4I. Okay, so now we can take any, if it's a certain problem where we're allowing for we're thinking about we're allowing for complex numbers to come into play, then we can simplify a principal square root with a negative number underneath, just a square root. Just a square root. Doing it this way. This would not work. This is not the case. Absolutely not. 2I to the 4th is not equal to negative 16. Minus 2I to the 4th is not equal to negative 16. Okay. So, with that, how would we simplify the principal square root of negative 25? Well, you take out an I. Okay. There we go. How would you simplify the principal square root of negative 12? Take out an I. So 4 times 3 is 12, so we've got 2I root 3. Okay, what about the principal square root of negative 13? Well, you take out an I, and now we can't simplify this any further, so that's it. All right. Now, here, what they talk about next is and this is where it kind of gets a little bit confusing, because it's you want to be able to say that I you treat I like it's any other number, and so you just go about the business like you normally would before you even learned complex numbers, and because you could do anything you learned before, you could just do that with complex numbers or imaginary numbers. And in general, yes, that is true. For the vast majority of cases, that is true. But there's some special circumstances where you can't. So if you've got these properties of radicals here, okay, like if you had the square root of, or the nth root of A times the nth root of B, you could combine those and get the nth root of A times B. Well, okay, we have to say that we're only allowed to do this, apply this property here, assuming n is even, we're only allowed to apply this property here if the numbers, the radicands are both positive. And, this is kind of confusing. It's like, well, why not? Okay, so like, what's wrong with this? And then writing this as minus 10 times minus 50 is positive 500, and going from there. What's wrong with that? Well, the problem is if you don't put this restriction on saying you can't multiply this as it is, then you're going to end up multiplying two negative numbers by like negative 1 times negative 1 and defeating the whole purpose of why you defined I in the first place. So you need a property like this. You need to be able to put this restriction to say, okay, wait a minute, we need to account. We can't do anything with this until we account for the I, that's the associated I. That's one way of looking at it. Another way of looking at it is that, so before we take out the I here, as this sits, okay, these are undefined, right? As they sit. It's not until we take out the I that they become legitimate. Like, you can kind of look at it that way. Like when we define the principal nth root of A, this radical, okay, well, it still has its original definition, to where, look, if n is even, then and you put a negative number inside as the radicand, then that's not valid, right? Well, you could kind of look at it that way, in the sense that as this sits, these are not valid, Like in any property that you're going to see as you go through calculus, etc., any property of like limits or derivatives, etc., that you could separate a derivative into separate derivatives. It's only if the derivative exists that you can do that. If it doesn't exist, then there's no property you can't apply a property to something that doesn't exist in the first place. And so that's how you could kind of look at this. It's like, well, as these sit per the original definition of radicals, as these sit, they're undefined. So you can't apply any property. But now we can make them exist by doing this. Now this is legit. We have an even root, a square root with a positive number underneath. So now we can go ahead and simplify this. So I squared. So let's see, this is 50 times 10, which is 5 times 10 squared. So we can take out a 10. So minus 10 root 5. I squared is negative 1, so minus 10 root 5. Okay, so that's kind of two perspectives you can try and view this from. One is that we have to apply this restriction here when it comes to applying a property like this, a radical property like this. And and this applies to the division the quotient property of radicals as well, because otherwise, if we don't apply this restriction, we'll be multiplying negative numbers together, and the negatives cancel out, and we defeat the whole purpose of why I is defined in the first place. That's one way of looking at it. Another way of looking at it is you can't do this until you make this a legitimate radical. Now we can say, but that's kind of confusing too, because then it implies that, well, if this doesn't exist in the first place, then we can't say this. If we come, let's see, we can't say this. We can't say, okay, well, this is equal to minus 10 root 5, right? But that is what we're saying. We're saying the principal square root of minus 10 times the principal square root of minus 50 is minus 10 root 5, square root of 5, the principal square roots. So it's however you want to look at it, but we'll get a better perspective on this and when we get to complex analysis. Just all you have to remember before you get to complex analysis, all you have to remember here, the only thing to remember is that if you're dealing with a square root radical, then you can't apply these properties here until you take out the I first. If you're dealing with a square root radical with a negative radicand, you can't apply these properties here until you account for that I. You apply the property where you take out the I. Now, if you have something like this, what would this be? Well, no, you can't. This doesn't mean anything. You can't do anything with this until we get to complex analysis and we start to learn more. Until then, there's no solution here because you have a negative radicand under an even root radical that isn't 2. No solution. But again, there will be, once we fully learn complex numbers and complex analysis, there will be a solution. Okay, so principal square root of minus 9 times the principal square root of minus 25. Let's apply that property. Okay, now we could multiply these, but instead we know the principal square root of 9 is 3, and the principal square root of 25 is I, so let's do that. So we've got 15I squared, that's negative 15. Okay, what about the principal square root of minus 15 times the principal square root of minus 3? Okay, let's take out an I before we do anything. Okay, but now here, let's go ahead and multiply apply the quotient property of radicals. So 15 times 3 is 45. So 9 times 5, we've got 3I squared root 5 minus 3 root 5. Okay. Now, what about this? Well, okay, it's the quotient property, so we can't. Okay. Still, we have to take out the I first. But now let's go ahead and apply so I divided by I is 1. Let's go ahead and do this now. That's it. So, I mean, that's what this is saying, that the principal square root of minus 50 divided by the principal square root of minus 2 is equal to 5. Okay. So, now, here they go ahead and officially introduce complex numbers that the textbook hasn't introduced the idea of a complex number yet. We just were introduced to imaginary numbers, that the pure imaginary number. But okay, here they officially introduced complex numbers. So yeah, we define a new set of numbers that includes the real numbers and imaginary numbers. This is called the set of complex numbers. Okay, and so yeah, it's a number in the complex plane, and the general way you look at this is kind of the default variable for a complex number is you say z, and then you're going to write it as a plus bi. Okay, where a and b are any number on the real number line. Okay, so a and b it's any real number on the real number line. That's it. Okay, and you call this is a general complex number. You can see how this represents any number in the entire complex plane. Any number. This is the way you can look at it. And this is the imaginary axis. This is the real axis. But this is you pick a real what they call the real part is A, and the imaginary part is B. So the real part and the imaginary part are real numbers. Like you're picking a real number off the horizontal axis and a real number off the vertical axis. That's the real number, the imaginary part. But the imaginary part is going to be associated with an I, though. Okay? Now, if you've got, as far as notation goes, we'll get more into this. We'll go into a lot more detail at the end of trigonometry on complex numbers. But we're going to go into a lot more detail in the complex analysis course, but we're going to expand on still do a good bit more at the end of trigonometry on complex numbers. But like the notation is, you can think about, you can have a pure real number if you're just on the horizontal axis. You can have a pure imaginary number if you're just on the y-axis. So if you had 2i, that's pure imaginary, but it's technically still a complex number. It's just 0 plus 2i. In the same way that the number 8 is still technically a complex number. It just has imaginary part 0, and here this has real part 0. But you can kind of say one way of the notation is that, like, or if you're on the horizontal axis, you have a real number. If you're on the vertical axis, you have an imaginary number. If you're anywhere in the plane itself, you have a complex number. That's kind of a notation you'll hear used, even though technically all numbers are complex numbers, even if it's pure imaginary or pure real. Okay, so now this a plus bi, this is the standard form of a complex number. So anytime you're working a problem that involves these imaginary components, the idea is you can do whatever you want throughout the problem. You can move numbers around, divide both sides by this, multiply both sides of an equation by this, etc. Multiply by 1 in the form of something, whatever. But when you get to the end, it's like you want to put the final answer in the standard form. You wouldn't want to leave a final answer like this. No, you want to put it in standard form. Like, even though when it comes to like variable expressions, we might leave something like this. There's no standard form. But when it comes to a complex number, you want to put it in this standard form here. Okay? And now, but it says that there are some exceptions in the sense that, so like technically you would, if you had 3 minus 2i, well, the real part is 3 and the imaginary part is minus 2. Right? Like the a plus bi, you can see what clearly what is the real part and clearly what is the imaginary part. Being the real is 3, the imaginary is minus 2. However, it's okay to just leave it like this. Right? It's okay to leave it like this. Also, if you've got, so the standard form is a plus bi, right? Well, what if you had, like they show here, 5 plus, and then the imaginary part was root 3. Okay, well, you get that. Well, it can be kind of confusing. It almost looks like the I could be in part of the radicand. So you're allowed to. There's flexibility. You're allowed to like do this if you want. Okay, so with that, let's simplify some expressions here, and then, but when we get to the end, let's put it in standard form. So we've got 3 minus principal square root of minus 100. Okay, well, we know we can simplify this here. We could take out an I. Okay, then the principal square root of 100 is 10. Now that's in standard form, so we're done. Okay, what about this 2 plus 7i divided by 5? Well, if this was just like if this was 2 plus 7 pi divided by 5, we might say this is fully simplified. I mean, it's just kind of personal preference. What looks more organized to you, right? Can't do anything else with this. We could separate it out into separate fractions, but I don't know. It's kind of, to me, I like leaving it as one fraction, right? But in this case, absolutely not. No, this is not fully simplified. We want to continue to put this in so we can see the standard form of a complex number. We can clearly see what the real part is and what the imaginary part is. Okay? Now, what about this minus 6 plus okay, so let's see. Let's simplify this. Take out an I. Okay, 9 times 2 is 18. So we could take out a 3. Okay, now let's see. Minus 6 divided by 9 plus 3i root 2 divided by 9. 6 divided by 3 is 2. Okay, so let's see. Minus 2/3 plus, and then so we can see the real part or the imaginary part clearly. Let's do this. And there we go. Okay. So now in the next video, we'll finish this section. What we're going to look at in the next video is different operations on complex numbers. So they're numbers just like any other numbers. So we want to learn, okay, let's make sure we understand exactly how to add them, subtract them, multiply them, divide them. Now you might be saying, well, but if they're just like any other numbers, why do we have to learn how to add, subtract, multiply, and divide them? Only because, yes, they do obey these properties of numbers, right? But the form of them is a little bit different, right? Here's a real number, okay, but here's a complex number. So it's just there's going to be some nuances that we'll have to deal with in certain circumstances. Sometimes there's going to be formulas or certain situations where, okay, there's these slight exceptions to how the normal formula would work, because it's just the number is a different form, right? How are we going to, okay, if we had 10 divided by 5, all right, well, that's 2. Okay, great. What if we had 2 minus I divided by 4 plus 3i? Well, okay, we can't just do it the normal way we did it with real numbers. We're going to use the same properties when we learn how to divide complex numbers. We're going to multiply this by 1 in the form of something, and we're going to use these same properties. It's just the mechanics are going to be a little different in some circumstances. Okay, see you in the next video.